Good evening, it's me again, Jean Louis Van Belle. I want to do a quick follow-up video on my previous one, which basically established, I wouldn't call it a new paradigm, I've been working it for a long time, but basically a model for what I call real quantum mechanics based on electrodynamics only. So there's no nuclear force, no gluons, no quarks, no whatever. I want to be quick because, yeah, 40 minutes from now, the match between England and Norway will start, and I absolutely want to see that. And secondly, is also this video is more focused on the visuals, created a lot of nice visuals, and we did some very substantial work on the model, extending it to heavy nuclei. So you can see the reference here. You can look on my channel, my physics channel. I have a few channels on YouTube. And as you can see in the this long lecture, an hour and 15 minutes, there I really go into the details of all the questions on a model like this. Why are electrons, protons, nuclei not radiating out their energy? If that energy is based on ring currents, electromagnetic, well, basically charges that go around and two in a flat or in a three-dimensional space mainly. The core shell architecture of the neutron, the math, and then interesting the packing that I explained in neutrons and protons. While one neutron becomes a deuteron, we have tritium with a triton nucleus, which is one proton and two neutrons, and then the basic elements for packing are alphas, which themselves are like for a core of two neutrons and protons, and they disorganize then in higher very, very stable cores, carbon 12, oxygen 16, and neon, with wonderful mathematical shapes. And the isotopes of all nuclei can then be modeled either as a perfectly packed nucleon, or else with satellites around it, another neutron that gets added, or a deuteron. So I said I won't be long, so that's the picture. It felt like a mountain over the past 10 days as we really extended this model to, well, I would say all of the elements, all of the nuclei, all of the isotopes. Let's go for it here. I said it's not new. That was in the previous presentation, but the nice thing is here it's animated. So we have a point-like charge going around in a 3D trajectory describing a perfect sphere. Dimensions give the impression it's a bit oval or ellipsoidal, but that's not the case. It's a sphere. In our real quantum mechanics, we interpret proton not really as a probability cloud or whatever. You can represent it by a wave function, but the wave function will really represent a position at some point in time in some point in space. So we have this here, a spatial current shell. This charge is point-like and has no rest mass. It requires relativistic mass because it whizzes around at the speed of light. Here we have the neutron architecture. We explained that also, but not with a nice animation, a static image in our previous presentation. We apply the same, what I would call equations of motion, as Dirac called it. Fields driving the motion of the charge, of the two charges, we think, a negative and a positive charge, giving the neutron an overall neutral electric charge, but giving it a magnetic moment that is basically resulting from a two-shell model, a compact negative core inside and a counter-rotating, because it's a positive point-like charge, outer positive mantle. So it maintains net neutrality, and the outer positive boundary is very, well, it's vital that the negative shell is inside a positive one, because that creates an electrostatic distance barrier in our model that prevents protons and neutrons basically from collapsing on top of each other. If we have the negative shell outside, then there would be a very strong attraction. The strong attraction in a stable nucleus between a proton and neutron now comes from basically an electromagnetic alignment of their dynamic magnetic fields, their magnetic moments. We explained that the strong force basically is a shorthand, or what would we say, a phenomenological description of electromagnetic dipole fields. Again, I need to go fast because I want to see the game between Norway and England. Belgium lost, unfortunately, but Spain played a great match yesterday. So here, that's from the previous one, proton and neutron coming together in a stable deuteron structure, the nucleus of a deuterium. And then you add, we forgot triton here. Did we? Yes, we did. Any case, triton, if you add a neutron on top of that, you have a coaxial structure, the proton inside, and then sort of like a sandwich with the proton between, two neutrons. And then you come at the real first building block of all other nuclei, and that's the alpha particle, the nucleus of helium-4. 2 protons, 2 neutrons in a tetrahedral structure. I put some graphs there that I also showed very quickly in my previous YouTube video and presentation. But yeah, we did the calculations. I refer to the papers, which you can find on my ResearchGate page. And I'll talk a bit about that now. We produced a lot of papers, technical papers, working out the model. For various isotopes. In the beginning, we used a sort of what I call a liquid drop or global blender model, which is actually quite common, but which really requires supercomputers to do the calculations. Especially when you sort of do away with what I call the phenomenology of the strong force, and you really use Maxwell's equations to model each and everything. What we found out is that this liquid drop model, where you sort of add a neutron or a proton one at a time and drop them in sort of a plasma of other neutrons and neutrons, that it's computational brutal. On my old laptop, I bought a new one. It required like 5 hours to do a simulation sequence. I bought a new computer, more powerful one, 16-core GPU, lots of RAM, hardware accelerator, NVIDIA GPU. It still took hours. So I realized I was not really getting very far. And the second thing was that we noticed that in a model like that, you can basically what comes out is stable. You explain the stability of isotopes, but the unstable isotopes don't get singled out. So you have an empirical challenge. A lot of isotopes are unstable, have very short lifetimes. So we realized that we needed to work on a different model, really using these building blocks. Modeling heavier, even light nuclei with these alpha cores, and then satellites around it, or more complicated alpha cores that get arranged in another core, like a lead core or a neon core or an oxygen core or a C12 core, and then the satellites, another neutron or a neutron and a proton, arranged or not in a deuteron structure, and that really worked. We had a sort of a matrix mechanics approach that showed the energy equations came out all right. And here you can go on my research page where I started with sort of a position paper, the electrodynamic landscape of nuclear stability from these global blenders, commonly used models, to incremental builders, where we focus on one isotope series to another, but first determine the geometry. We built confidence with silicon. It's a light isotope, but not as light as oxygen and carbon, which we already had. Model worked perfectly. We then formalized the math a bit more, really matrix operator formalism. It works beautifully well, matrix mechanics instead of wave mechanics. And then we started working on what we call sort of matrix mechanics and network graph statistics. We applied that to oxygen, and that worked also beautifully well. And so then we started real work. Again, fine-tuning the position paper for what we call a sort of a scaling to macronuclear architecture. We basically heavier isotopes, and then we did it for first for silicon again, worked fine. Code is stable, and then we worked on. First we jumped to uranium, wonderful, and then we went back to medium mass nucleons in the calcium series and the iron series, not only calcium 40 but all of its isotopes of calcium, and then iron 56 and all of the isotopes of iron. So I sum it up here. Instead of tracking a nucleon, what we did basically across millions of possible continuous spatial grid points, we track only the physical loops themselves, which we put at fixed positions based on trying out different geometric arrangement. So space really collapses into discrete linear algebra matrices, 28 by 28 nucleons that interact with 28 other nucleons, with 27 others, one out of 28 that interacts with the 27 others, so that it's a 28 by 28 matrix for the mutual interaction, electromagnetic interaction, 40 by 40 for calcium 40, and 41, 42 for the isotopes, and so on. 56 by 56 for iron 56, 238 for uranium. But again, these matrices expand or become a little bit smaller depending on the isotope for these elements. The calculation that used to take hours, even on the new machine, now execute on, it's still a standard laptop, cost 2,000 euro. It's a high-end gaming computer basically, but it runs in seconds, I'd say, minutes for sort of longer combined iterations, not hours. We proved that because we went through the whole table of elements over the past 2-3 days. The algorithm is referred to, I found it out actually a bit later because we built it up from scratch, but apparently it's in the class of these, is referred to as a limited memory Broyden-Fletcher-Goldfarb-Shano with bound constraints optimization algorithms. And don't worry about trying to pronounce it. As I said, what really matters is it's quasi-Newton, I would say, Newtonian relativistic physics combined with Maxwell's equation in an optimization routine. So what does it do? I will show that a little bit. It really tracks hundreds of angular variations. We use the variational principle. What if you change this degree of freedom a little bit? What is the impact on the others? And optimizing each and every one until we find a stable equilibrium for everything, for the whole nucleon. So we see data, quote here, high energy chaos, what we got out of the global blender, or the liquid drop model wasn't high energy chaos, but it didn't weed out the unstable isotopes. So that was basically the problem. So we have a simpler algorithm that does do that, which both is in conformity with stability, instability, explains the stability of instability of isotopes. I will talk about that for calcium specifically because there's something really funny there. Our algorithm explains something that modern quantum theory can't explain in these in their optimizing, in their liquid drop models with a strong force. We find stable geometric valleys or configurations, I would say. Silicon, as said, we tested various models and code, and the optimization mechanisms, on silicon 2 or 3 times when running sort of what I call an orientation solver. It's the matrix configuration. We found immediately this matrix showed naturally factorized, I would say, alpha blocks in a specific position. I'll talk about the Fiedler vector in a while. Not in detail though, but it's kind of a measurement of how strong a network hangs together. And we calculated, it's a network graph metric. We calculated and confirmed that sort of this point group packing really emerges natively from the electrodynamics that we have in our matrix mechanics. Although I show this very quickly, this is for the first table, determining the position when you add an extra satellite, an extra neutron here in the case of silicium 29. So silicium 28 is nice, geometric. Here we add a neutron, and our algorithms show that the binding energy is negative. It's probably not normalized here, I guess. It's normalized, but not in the units you'd expect, mega electron volt, kilo electron volt. But yes, that there are only 2 stable positions at the poles, opposite of each other. So there's 2 configurations there, nicely symmetric, that are possible at all for silicium 29. So I said that matrix and all the optimizations, well, there are a number of matrices, really angle, matrices with angles, matrices with energy, measuring the binding energy or the electromagnetic coupling between these nucleons. So it goes from a silicium 28, 28 by 28 matrix to silicium 32, the 5 isotopes. You have them there, which then have a 32 by 32 matrix, and there's the spectral graph radius, again, that's not a physical radius expressed in femtometer, but one of these metrics that show what happens. The Fiedler value, I won't go into it, but shows, that what happens in sort of these optimizations. So we have lots of data at each node. We get data, angles, energy, and whatever. I show here angles for optimized angular gradients, theta and phi for the tilt and the yaw, as we call it in a network. Calcium 40 then, I said again, we have these liquid drop formulas. They lead to a very bizarre contradiction if you Google on Wikipedia. They basically, out of all these algorithms, and I said we used the liquid drop formula as well, it comes out that calcium 40 should actually be unstable, but it's the most abundant isotope of calcium in nature, and it's highly stable. Our liquid drop, this is actually wrong. It relies on theoretical liquid drop formulas, not empirical ones. Well, empirical ones in the sense that they introduce this phenomenology of the strong force. I said phenomenology. So in that sense, it's empirical, I guess, but they use them as fitting parameters basically more than as really empirical values. Again, I'm rambling a little bit, but if you've seen the previous video and our previous other videos also, you will understand what I'm talking about. Our matrix solver solved that problem, a theoretical problem, so in that sense it's already a great success that our RealQM, real quantum mechanics, predicts the stability of calcium 40 while quantum mechanics since the 1970s, the introduction of the strong force in the Second World War basically says that calcium 40 should be unstable, yet it is stable. In our model, we have 10 alpha cores that lock into a perfect square anti-prism ring, it is called technically, apparently, with dual axial, that's the technical name, but you can see it's sort of two prismas that lock into each other, and yes, have a cap related to relaxed connectivity. We optimized, provides really geometric proof. That's sort of the graph you show, and underneath it's that Fiedler vector. Well, actually, it's called the graph Laplacian Fiedler value, and you can see that it reaches a maximum at calcium 40. Iron, next element, it really represents the, it's very, very nice. We all know that it's the maximum binding energy turning point that you have in cosmic nucleosynthesis. All becomes iron. It's if you want to fusion reactions that turn iron or lower isotopes, lighter isotopes or nucleons into heavier elements, that starts consuming more energy rather than producing it. It's a beautiful shape. We have a central alpha core enveloped in a 12 alpha icosahedral shell. I didn't know how to pronounce the word. I had to look it up. I worked with with AI, you can see, to sort of name all these shapes. It's insulated by sort of an internal buffer sheet. These are the stars, and that's the electrodynamic anchor for all iron isotopes. If you introduce a 57th one, as you can see, we have a very unstable isotope. The Grab connectivity curve plunges to almost zero. Really interesting. Lots of unstable isotopes of iron, very particular graph connectivity curve. Uranium. I said that was beautiful. We sort of did this in an hour. Adapting the basically the number of iterations, finding a shape. Here we have a sort of lead, really lead, Pb, core protons and neutrons at the core, and then a lot of fringe satellites and two really interesting neon 20 polar caps. I said neon is also sort of that building block. Here we did some optimization, which you can see in the, well, that's an optimization we do in everyone. The phase locking, making sure that everything adds up to, a multiple of Planck's quantum of action, and that the phases are optimized electromagnetic fields, that they are perpendicular one to another for so many nucleons. It's an amazing algorithm because we solve here a very, 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 very complicated multi-body problem, basically, three-body problem. As you know, in classical mechanics is already difficult to solve. We did it for the Triton, using the laws of electromagnetics. And heavy element, 92 protons, 476 angular degrees of freedom that you have to handle. We introduced, this is interesting, has to do with the non-radiation condition, I would say. Electromagnetic field changing electromagnetic field travels at the speed of light. So when something changes at one end, it travels to the other and creates, well, a disturbance there, or an effect, an electromagnetic effect, with some retardation. And that's sort of where the scale of these models, really the radius or dimension of a nucleon becomes important. And read the paper. I basically show that nucleons can't go too large, can't grow too large, because across 7 femtometer, I forgot that here, 7 femtometer radius, you really have wave frustration, all kinds of phase unlocking, I would say, which creates wave frustration, as I call it, basically a tangled mess. It then isolates the polar caps and basically falls apart. I call that a preformed fission channel, but it can fall apart in a lot of ways, basically. These fission channels are again established from first principles, plain electromagnetics. 29 isotope cascade. Yeah, we have 29 isotopes from uranium, as you know, it's a lot more. And we swept through that too. A very interesting graph connectivity curve with a stability apex at uranium 230. And I explained sort of the bumps and up and downs in that curve in my paper on uranium, on using this new engine, as I call it, nuclear engine or nuclear engine for calculating all these this nice stuff. I'm almost there, and it's 11:15. I'm at 25 minutes, really good, less than half an hour, because this is the last slide. This is sort of where we show dynamically how these, well, one of the optimizations work, the what we call the angle relaxation pass. The I said when we do this optimization, we don't distort the underlying positions in 3D space, but we target only the continuous angular degrees of freedom. Well, with steps, of course, there are lots of steps. I let Gemini, with whom I worked a lot, write the caption for this. It sort of says, look how the system cools down. It doesn't cool down really, but yeah, it starts from an orientation chaos. All these angles are in a random direction. That's the initialization of the iteration. And then we let them independently tilt, twist, to maximize mutual induction. Frame by frame, I would say. Well, it's frame by frame in this animation, but it's also frame by frame. For each of these angular positions, so there are two, yawn and tilt, until they really lock into a perfect phase-locked anti-parallel position, pairs, which drop the network then into its lowest energy attractor state, really the base state of the nucleus. What was nice is that we also modeled excited states of nucleons, but you can read about it in the papers. So the LBFGSB engine, forget about the abbreviation and what it means. But it holds these coordinates. We hold the coordinate centers rigid to prevent numerical drift, the liquid drop model. But yeah, the relativistic phase retardation effect does introduce a dynamic spatial scaling effect. And so it does lead to, changes in the position, in the sense that we have a sort of the global for all of the nucleon positions for these shells, a contraction, physical contraction. So that's it, basically. All of the charge and these protons and neutrons, the dual charge and currents. Well, the data we get out of our engine matches empirical already also, and the binding energy we get is real world binding energy. First to page 8 of the paper there. There's lots of annexes, and I think that's really it. I'm at slide 13 of 13. I thank you. It's a short lecture or short video. Less than 30 minutes. Probably a bit. Probably I'm talking a bit fast. That's because I'm tired. But also I wanted to get this out of the door, and so please visit my ResearchGate paper and check it out. You need to say that also. All of the code I use is on GitHub, GitHub/Jean Louis Van Belle, and you can download it. Run it on your own machine, and it's kind of nice to build the nuclear world, I would say, with that code. So try it out, challenge the model. I think it's very difficult. We challenge it ourselves. One thing I would say is that to build all of this, I could not have done it without AI. A remark on that, I found ChatGPT pretty useless. It just didn't get the physicality of the situation. Gemini did great. DeepSeek did very well as well. But DeepSeek did sort of, took me quite a lot of time to debug the code, change it. And what I also find is that DeepSeek does sort of introduce what I call fitting of parameters, or skips or introduces optimizations that aren't physical. Gemini was a lot more honest, so I can understand why its market share is growing so quickly and why ChatGPT is losing market share. Gemini is great. From the three, ChatGPT, DeepSeek, and Gemini, I warmly recommend Gemini. I was on the free version of Gemini also. Well, I cancel now my subscription to the Go version of ChatGPT, exactly because I was so disappointed in it always also coming back with defending mainstream theory. It just didn't get this kind of stuff. Okay, with those remarks on AI and how I worked with it, I explained it also in the papers how I work with AI. It really did involve triangulation, I would say. I call it the AI triad between three AI platforms to arrive at what I have, something that is really nice, simple, built up from first principles. Einstein's mass-energy equivalence relationship as the mass-generating principle, Maxwell's equations, and then the Planck-Einstein quantization law, all neatly tied into classical matrix mechanics applied to quantum physics. I will end here. I wish you a very nice evening. And now I will prepare for the game between Norway and England in the World Cup.